as I have mentioned, it's very useful in many problems where the geometry of the fluid flow is cylindrical or similar to cylindrical. Then it's convenient to use cylindrical polar coordinates for our computations and calculations. And therefore, in the standard format, the cylindrical polar coordinates corresponding to x, y, z in the rectangular coordinates are taken to be r, theta, z. R is the variable in the radial direction, theta in the angular direction, and z or z in the z direction. And these three, by convention, if r is the radial distance from the origin to some point P, theta is the angle. And remember that if nothing is mentioned about theta, the positive direction of theta is considered to be the movement, the angular movement in the anti-clockwise direction. So theta is considered to be positive in the anti-clockwise direction. ER is a unit vector in the radial direction. E theta is a unit vector in the theta direction or angular direction, and likewise Ez is a unit vector in the z direction. If the motion is two-dimensional, then we know it from our trigonometry that the radius r is given by under root x square plus y square, where x is taken to be r cos theta, y is taken to be as r sin theta, and tangent theta is equal to y over x. These are very standard formats, very useful for our computations for appropriate geometric conditions. The continuity equation will then take form as delta rho by delta t plus 1 over r times partial derivative of this into rho ur over dr plus 1 over r into delta rho u theta by d theta, and partial derivative with respect to z of rho times u del. So this is continuity equation in cylindrical polar coordinates r, theta and z, and it's used a number of times. If we try to show it in a diagram, then again, as usual, you can see for the two-dimensional motion, if x and y are rectangular coordinates in a plane, then we convert them to cylindrical coordinates and they will be r and theta. Simply r and theta, because it's two-dimensional. And r is in the radial direction while theta is in the angular direction. And if there is a movement, as shown here in the diagram, the positive direction of theta is always taken in the anti-clockwise direction. And we continue with that. So this is the format. This is the coordinate system in two-dimensional, where in the three-dimensional motion, we will have another coordinate coming in, that is the z direction. And therefore, if you try to figure out x, y, and z, these are three rectangular coordinates that are mutually perpendicular. And if we want to transform them to cylindrical polar coordinates, then we can see the radial component, the angular component u theta and uz, that is perpendicular to both r and theta. So this is the situation in three-dimensional motion for cylindrical coordinate, and the continuity equation can be transformed by standard procedure in three-dimensional also and written from rectangular form to cylindrical polar coordinates in 3 dimensions, just as we wrote down in 2 dimensions.